Hi everyone, and welcome to a video about the t-distribution and the chi-square distribution. Our goal here is just to go over the basics of the two distributions and see how to look up critical values in Excel. So starting with our student t-distribution, we have this formula that it's based on. You don't have to worry about this formula for confidence intervals, but it will come up when we go over hypothesis testing. You can see from the formula we're comparing up here an x bar, which is the mean for a sample, and mu, which is the mean for the population. But we're using the sample standard deviation to do that, and that's a special ability of the student t-distribution. Because we're using the standard deviation of a sample, we're going to be stuck with the same degrees of freedom that we had when we calculated the standard deviation of a sample. If you remember from way back in the day, that was n minus 1 in the denominator when we were doing our formal calculations for a standard deviation. The long and short of it is, don't worry about this equation until you get to hypothesis testing. And this is one more thing to input into Excel. If I have a sample with 18 pieces of data, then the degrees of freedom is just 17. And Excel will ask us for a degree of freedom pretty clearly, so you don't have to worry about having to read anything complicated or do any complicated math. Let's go over some of the basic properties of the student t-distribution. The first is that the student t-distribution is different for different sample sizes, and that comes back to the degrees of freedom and the fact that we're using n in the calculation for the equation that builds the student t-distribution. Since the sample size is sitting in here, changing the sample size will change the values of t, which will change the way the whole curve looks. Good news is, in general, it still looks the same. It will be a bell-shaped curve, just like the standard normal distribution that we're used to. It will still sit over 0, just like the standard normal distribution that we're used to. The big difference will be that the standard deviation is not 1. In general, it's greater than 1. As the sample size increases, the student t-distribution gets closer and closer to the normal distribution because its standard deviation will get closer and closer to the number 1. So looking at some different graphs here, we see the blue curve is the standard normal distribution. The red, that is very close to it, is the student t-distribution with 12 pieces of data. And the orange that is much further from it is the student t-distribution with only 3 pieces of data. So as we increase the pieces of data in our data set, we get closer and closer to the standard normal distribution, but we don't quite ever make it there. We would still sit over 0, and our standard deviation will be close to 1, but never quite 1. And you may be wondering, why do I care about all that? That seemed complicated, and you care about that because we're going to use it to create confidence intervals and to do hypothesis testing. To be able to do that, we've got to be able to come up with critical values for this distribution. And luckily, Excel has something built in to help us out with that. So some of the books will use this T sub C notation, and some of them will use the T sub alpha over 2 notation that we saw before on this slide. It does not matter. Don't bother yourself with the notation. What we want to focus on is how much of the data is in the middle of the graph and how much is on the outside, because we've got to find these two values that cut off the tails from the main part of the data set. This will be the same way that we've calculated critical values in the past. So I've got to be able to figure out how much is in this tail. I've got to input that into Excel so that it can give me back this value down here. So let's go over to Excel and try that out. Previously, when we did calculations in Excel, it was based on the normal distribution, and we would use equals norm.dist. We're now dealing with the t-distribution, so instead of equals norm, we'll say equals t. And you can still see dist and inverse come up. In these cases, for critical values, we're given the area on the inside of the curve, and we're looking for the values on the bottom of the curve. Since we're given the area on the inside of the curve, I'm going to go to t.inverse. And I'm going to tell it the probability on the left-hand side, just like I did before. So for this value right here, the probability on the left-hand side is 0.025, because we were looking for a critical value related to a 95% confidence interval. For a confidence interval, the percentage is always going to be right in the middle of the graph, giving us 2 separate tails. So I can enter 0.025 and then the degrees of freedom. I have to go back to the problem and see how many pieces of data I have when the sample size is 15. Degrees of freedom, as we said before, is just n minus 1, so it's 15 minus 1, so it's 14. Entering that, we can see we get the value on the left-hand side. Negative 2.145 is how they've rounded it, and we're very close to that value. So let's zoom in and we'll do that calculation one more time for the right-hand side. On the right-hand side, the area to the left is much larger. It's this 0.95 plus this 0.025. So we can get that two different ways. We can say either t dot dist, inverse, of 0.95 plus 0.025, or we can just say 1 minus 0.025. Either way, we would get the same value. So 1 minus 0.025, the opposite of what we inputted up here. And the degrees of freedom will be exactly the same, 14, because it was 15 minus 1. You see they get the positive value. And you'll notice that this is a symmetric curve, and it's centered around 0. So you really only have to figure out one or the other. Whichever one you're more comfortable with, the other one will be negative or positive. So if I was more comfortable figuring this one out, then all I have to do is make it positive to find the generic critical value. Or if I was more comfortable figuring this one out, then I have the critical value here. You'll see that you always need the positive one when you're doing the calculations for a confidence interval because of the way we add and subtract. If you use a negative one, you'll get the same values, but they'll be reversed. So technically you just have to make sure that you've double checked to make sure the big number is on the right-hand side and the little number is on the left-hand side when you make an interval. And I'll show you how to deal with that calculation in the example video. All right, the calculations for the t distribution are extremely similar to what we've been doing for the normal distribution, so this video will mostly focus on how to deal with the chi-square distribution, which we'll see is significantly different from what we've dealt with in the past. So moving into our chi-square distribution, we have a new calculation for this, and it is this calculation right here. We have the Greek letter chi, which just looks like a fancy x squared, and it's based on a relationship between the standard deviation of the sample and the standard deviation, or variance in this case, of the population. We're just making a comparison between the two so that we can calculate some information about a hypothesis test and about confidence intervals. Because we're once again based on the standard deviation of the sample, we're going to deal with the same n-1 degrees of freedom that we dealt with before. Two things to keep in mind is that the chi-square distribution is in fact squared. So when we go to our properties, we will see that it's not symmetric. The shape of the chi-square distribution depends on the degrees of freedom, just like it did with the student t distribution. And as the number of degrees of freedom increases, the chi-square distribution becomes more nearly symmetric, but never quite symmetric. And then because of the squareness of it, we will never have negative values, All of our values will either be 0 or positive, which is what this non-negative means, that they'll either be 0 or positive. So if we look at some of the graphs for the chi-square distribution, we can see they look a lot different from what we're used to, except maybe this purple graph, which is a little bit closer to what we've seen in the past for a normal distribution. It looks a little bit symmetric, but still not quite. You can see this tail touches completely where this one seems to go off into infinity. So the purple graph is a chi-square distribution with 30 degrees of freedom, meaning there's 31 pieces of data in this data set. The blue graph is the chi-square distribution with only 2 degrees of freedom, meaning there was only 3 pieces of data in this data set, and you can see it is far from symmetric. It's going straight up, never going past into the negative numbers, so just going straight up here. Our pink distribution is slightly more symmetric, our orange a little bit more symmetric than that, and our green a little bit more symmetric than that. And you can see the difference between green and purple is a whole 15 degrees of freedom. So it took quite a bit to make it from this green, not quite symmetric, to this more symmetric purple graph. So things to keep in mind is that because it's not symmetric and because it's not symmetric around 0, we'll actually have to calculate a right hand and a left hand chi-squared value, which means that we can't use our cool trick to just switch it from a positive to negative. We'll actually have to calculate them separately. And they won't look as similar to us as our other values did. They're going to be a little bit further outside the box. So we'll get values like 8 and 31, which is not something we've gotten in the past. Something else to keep in mind is that if you look at the degrees of freedom for these, it's pretty close to the center of the graph. So if I'm looking at a chi-square distribution with 30 degrees of freedom, and I'm expecting values to be up here by 50 and down here by 20, because 30 should be pretty much the middle of the graph. If you go back to the pink graph with 5 degrees of freedom, you can see 5 is very near the middle of that graph. 10 degrees of freedom, 10 is very near the middle of that graph. And 15 is very near the middle of the green graph. What that does for us is at least give us an idea of whether or not the values we got made sense. So if I'm looking for a chi-squared distribution value on the right, then it should be higher than the degrees of freedom. And if I'm looking for one on the left, then it should be lower than the degrees of freedom, since the degrees of freedom are going to be very near the middle of the graph. So let's go ahead and try an example. Let's look up some values using Excel. So a simple random sample of 19 IQ scores is obtained. And the construction of a confidence interval for the population standard deviation requires the left and right critical values for a chi-squared corresponding to a confidence level of 95%. The confidence level is related to how we're going to fill out our confidence interval. But what we really care about right now, since we're just looking for the critical values, is this 95%, meaning that 95% of the data should be in the middle, and we're looking for the outside 2.5% on either side. The sample size is n equals 19, so our degrees of freedom will be just 18. Leaving this and going over to Excel. When we were looking up values for the normal distribution, we said E equals norm. When we were looking up values for the t distribution, we said equals t. And now we're looking up values for the chi-square distribution, so we're going to go with equals chi, chi, squared SQ. Now, they've given us a percentage, which means that belongs on the inside of the graph. Since I'm using values from the inside of the graph, I'm going to use the inverse function. And I'm going to give it a left-hand value. So since 95% of the graph is in the middle, that's 5% left over for each of the tails, which means that each tail gets only 2.5%. So 0.025. And the degrees of freedom is again n minus 1. They told us n is 19, so this would be 18. Now I have to find the other side. I can't do the cool trick of just making this one negative or positive because I don't have the symmetry to work with anymore. But I can use this cool trick of using this chi-squared inverse on the right. And then all I have to do is type in the same exact value that I used before, 0.025, and the degrees of freedom, and I will get the value on the right. So knowing that our degrees of freedom is 18, I can double check that I got a value below 18 for the left-hand tail and a value above 18 for the right-hand tail. Moving forward in the slideshow, we can see that this represents the values from this distribution here. Did not want to do that from the beginning. Try that again. So I have values on the right and values on the left. I've got an area of 0.025 on either side, and thanks to the built-in on the right function for the chi-squared inverse, I no longer have to do a 1 minus trick, although I can. It will work fine if I do, and I can show you that in just a second. But I can just use the exact same value for either one, as long as I switch which chi distribution I'm using. Chi-squared inverse is going to be on the left, and chi-squared inverse .rt is going to be on the right. So going back to using just the same chi-squared inverse that I used before, I can use the same trick that I used before with a 1 minus. You'll see these two values match, so it's up to you. You can use the same exact function and always follow your 1 minus rule for the right-hand side, or you can use this extra built-in function to just deal with the right-hand side. Either way, you'll get the same value. So let's try that one more time. Find the chi-square values that separate the middle 99% of the distribution from the 0.5% in each tail. So if 99% of the graph is in the middle, that means 1% of the graph is left over for the two tails on either side, which means that only 0.5% is in either side. So these are the two values we should be able to find using Excel. Go ahead and clear out these values. Equals chi-squared inverse, because they've given me a percentage, and 0.99 is in the middle, so that means 0.005, 0.5%, is on the left-hand side, And in this problem, they've given us the degrees of freedom. So you got to watch out for that in the homework. Sometimes they'll give you n and you have to do a 1 minus. Or sometimes they just give you the degrees of freedom directly and there's no more math to do. You just type in there 18. So this is the value for the left, and we can see that it matches the one from the slides. And then again, I have two ways of finding the value on the right. I can either copy paste this and add my 1 minus, or I can use that built-in on the right function and put in the exact same value and the degrees of freedom. Either way, I'll get the same value. And they match the value from the slides. All right, so there will be a further video on how to use these values to create your confidence intervals. But for now, I just wanted to focus on what the two distributions look like and how to find their critical values in Excel.